So, welcome back, everybody. The second main topic for the computational science, and which includes machine learning and computational or numerical mathematics, computational science, computational physics, is about deep learning methods. And the topics which I am suggesting, if we now go into the basic list where you find, if you go up to the right corner here and you look at this comp physics link here and click on that one, you will be directed to the kind of overview list of the weekly topics. So you will find the material which we covered during the fall semester. And the idea now, or the suggestion now, is actually to look at the basics of deep learning methods. So the first two sessions which we're going to have now, they will cover the basics of neural networks and how we can build a neural network code and what kind of software we have. And we are going to link that with the solution of differential equations. Now, when we're done with that, the plan is to move on to a set of neural networks which are extremely useful if you're dealing with classification problems in particular, but you can also use it for regression problems, and that's convolutional neural networks. And then we are going to look at the convolutional and recurrent neural networks. So recurrent neural networks are ideal, for instance, for analysis of time series, if this is something which some of you may end up doing. And then if we have time and if there is an interest for that, we can look at other types of methods which are based on essentially the idea of neural networks. And these are variational autoencoders and general adversarial neural networks. And finally, we are going to dedicate some time to unsupervised learning approaches. And one of the kind of basic methods, which already many of you used in the studies on project number 1, is to use the principal component analysis and also to scratch the surface of clustering methods. So this is roughly the plan for the 2 next coming months. We are still pretty flexible with the deadlines for the projects, but obviously, since we're going to grade everything by the end of the semester, we would most likely appreciate if we could have everything by the end of the semester so we can actually grade the different projects. And thanks to all of you for project number 1. I was the projects were just fantastic. So you're going to get a feedback pretty soon on project number 1. Let me now say a little bit about neural networks here. And unless there are any questions, things which are unclear, I mean, again, use the chat function, or if you wish to unmute yourself, feel free to do that. So what we are going to start looking at is actually neural networks. So let's take a look at neural networks here. And let's get started. So if you now look at the basic topic for today and for next week, is actually to set up the basic mathematics, which are given by affine transformations. And these affine transformations are transformations where we essentially deal with dense matrices and dense vectors. And at the end, we end up dealing with matrix vector, matrix multiplications. That's the basic mathematical operation which we're going to do. And this is going to be linked with an algorithm, which is called the backpropagation algorithm, which allows us to learn the parameters of the model which we have chosen. Now, the model which we have chosen is going to be given by the architecture of a neural network. And that could contain a certain number of hidden layers and nodes in every hidden layer, or neurons as we may call them, also units. So I'm going to use this kind of notation or naming interchangeably. So I may use node, neurons, or units to indicate the elements of a given hidden layer. Now, if you look at the basic plans here, so the plan is, as I said, to build our own feedforward neural network and then play around with it a little bit and also give you an introduction to TensorFlow, which is an extremely useful library, which can be used with all kinds of deep learning algorithms. So TensorFlow was released by Google back in 2015, and it has also a very useful API, which is called Keras, K-E-R-A-S, which makes often life much easier when you want to set up a given neural network. There are some useful texts, and again, the text by Goodfellow et al. Has a chapter 6 and 7, and also chapters 11 and 12 contain a lot of material on practicalities and applications. We are going to discuss many of these topics here. There's also Bishop's chapter 5, which is also a pretty decent read. If you're looking at more hands-on approaches to neural networks and how to use TensorFlow, then this book by Aurélien Géron is also a very useful text. And in particular, then chapters 10 and 11 are those which are most relevant for getting started with these kind of approaches. If you're interested, there are some useful videos. There's one on the backpropagation algorithm, which we're actually going to discuss today. So the main topic today is to set up the basic mathematics of a neural network and to start setting up the algorithms for solving and studying neural networks. And then we're going to go a little bit back and forth. Next week, we will also look a little bit at the mathematics of neural networks and some other technicalities. And obviously, we will study the limits and the pros and the cons of dealing with deep learning methods. Now, what changes now from what you did before is that we are going to let the algorithm learn the parameters of the model here, which means that in contrast to what we had in linear regression or support vector machines or logistic regression, where we have pretty well-defined mathematical algorithms based on matrix inversion or solving a convex optimization problem. Now we are really encountering what you might call an approach where we let the program or the algorithm, or you could say the computer, to learn the model. Now, just to give you a kind of small digression before we move on, if we look at what we did in project number 1, when we set up a model for a polynomial, we wanted to make a fit, and we assumed, for instance, that we had a 5th order polynomial that was fed into a linear regression algorithm, and we could then obtain the optimal parameters for a 5th order polynomial. Now, you could think of doing that with neural networks as well. So you could actually feed in a design matrix, which is now given by a model of a 5th order polynomial. So you could say that, okay, I want to use this 5th order polynomial because I was so successful with linear regression. And now I want to use a neural network to find the optimal parameters of a 5th order polynomial. Now, this is okay, and you can do that. The only problem then is that you're taking away some of the flexibility from a neural network. So in a neural network, what you would do is actually to feed in just the input parameters, and then you would let the network find the optimal function which describes your output if you're dealing with a regression problem. So in a certain sense, this is slightly different from the kind of approach where our model was something which we decided upon when we did linear regression. Now, in linear regression, what we would do then would typically to mount a problem with a given polynomial degree of freedom, if that was the approach we wanted. Whereas here, the model is going to be given by the architecture of the neural network. But you could also feed in to the neural network a kind of guidance. So you could say if you believe that your model is best described by a fifth order polynomial, you could actually feed that into the neural network and let the network find the optimal weights or parameters of the model. But in general, what we are going to do now is to use something which is called the universal approximation theorem, which is a central theorem for neural networks. And that simply states that a neural network with at least one hidden layer can approximate any nonlinear complex function to a given degree of precision. It doesn't say anything about the complexity of the network, whether you have 1, 2, 3, or many hidden layers, and how many nodes there are, what kind of approximations you're making to the setup of a neural network, and so on. It simply states that with one hidden layer, you can show that the neural network can approximate any nonlinear function to a certain approximation. So let's switch a little bit now back from the slides here to the whiteboard and start looking at the basics of a neural network. So I'm going to mainly use the whiteboard for the rest of the lecture here so that we can set up the basic elements of a neural network. So let's switch screens a little bit. And please feel free to ask questions, interrupt me if there are things which are unclear. Never hesitate to ask. So I'm just going to switch back to the to my whiteboard. And we are going to look at the basic elements of a neural network. So let's try to bring it up here. So the basic elements. And I'm going to use the shorthand NN to label a neural network here. Now, if we look at some of the central elements here, the way you can look at a neural network is that this is given by a set of mathematical operations, which are essentially given by matrix or matrix vector multiplications. But let's start looking at the basic elements here. So what we would typically have is something which we call an input layer. And this is normally defined by what we discussed before the break. This is normally given by the design or the feature matrix. And we call this object X. So if you are typically having an image has normally 3 dimensions. It's going to be given by the pixels for the height and for the width of the image. And then there are going to be color channels. If we now just deal with an image without colors, you would simply have the height and the width given by the pixels. So a typical image could have 64 times 64 pixels. You can reduce the dimensionality to, let's say, an image of, you can make a very blurred picture, and you could have an image which has 8 times 8. And the typical image then would then end up with having 64 pixels, and they could define your inputs. Then what we are having next is a hidden layer. That's the next step. We have a hidden layer with given nodes, with a given number of nodes. So nodes, or I'm also going to call them interchangeably neurons or units. And then at the end, we can have more than just one hidden layer. So I'm just going to put an S here to indicate that we can have several hidden layers. And clearly, the more we have, the deeper the network. So when we talk about deep learning as a common denominator for these kind of methods, what we actually do mean is that we can have pretty complicated neural networks with many, many different layers. And we will see that when we move on to convolutional neural networks, that there are several mathematical operations which can be represented by different types of layers. And then finally, we have the output layer. And the output, that is where we compare what the network has produced with our targets. So here we compare with the ideal, what we want to reproduce, compare with our targets. So I'm going to make a kind of drawing now of a simple network, and I'm going to use that one to introduce the different parameters which are going to encounter. So a typical network with one hidden layer looks like this. So we would have an input layer here. And we can have different inputs. We could have an x1, x2, down to some xn. The number of inputs do not need to be the same as the number of nodes in a hidden layer or the number of outputs. So if I'm feeding in an image with 64 pixels, then this image will then have 64 inputs. However, the output may just be an image. And this could be the number 1, it could be number 10, or it could be an image of a cat, or it could be a function function value which I want to reproduce. So the x's could be the coordinates of a given system. And these coordinates for a high dimensional problem, they could just produce one single output, which will be the final function value. So we are going to indicate this with different nodes here. So these circles represent different nodes. And then if we have just one hidden layer, you can have a given set of nodes here. And I'm basically going to label these nodes with an H for hidden. And you will have a superscript here, which I'm going to call for 1, because this is the first hidden layer. And so this can go on down to an H of M here for the first layer. And these will also be marked with these given circles. And then the final one is our output layer. And the output layer could just contain only one output. So if I'm looking at an image or classification problem, all these different inputs, they could conspire to produce one single output, or you could have many outputs. So I'm going to label the outputs in the kind of notation which we're going to use throughout the description of neural networks is we're going to reserve the variable y for that. I'm not going to put a tilde on that one. And then I'm going to use the value t for the targets. The targets are the data which we want to reproduce. So we can have now a output node y2 down to some y of k. So we can have several nodes or just one. So these conspire to produce an output, and these are then compared with the targets. So to be compared with targets. And now I'm going to use this letter t of I. So that's the final value. Previously, when we did linear regression, we dealt with a variable y, but now I'm just going to use t for targets. So if we are doing a regression problem, the typical cost function could be the mean squared error. So in a regression problem, our cost function or risk function could be the mean squared error. So we would have the mean squared error, and that would be a function of 1, and I'm just putting 1/2 here, because then we get rid of the factor of 2 when we take the derivative of this quantity. So this is a quantity we want to optimize. And this would now run over all the data which we have. And we would compare the output of the network with the targets. So that could be a typical cost function. Later on, we are going to look at a typical cost function for a classification problem. And the thing now is that when we are setting up this specific network, what we will have then is a connection between the different nodes. And these connections are then represented by what we normally call weights and biases. So let's bring up the connections. So this input node normally connects with all the hidden layers, the hidden nodes which we have. So I'm going to mark that one with all the other ones. So the X2 connects with all the other nodes here, and so forth. So I'm not going to draw all the arrows here because then it gets pretty messy. Now, each one of these will now have a connection with the hidden layer. And this connection is now represented by a weight, which I'm going to call W11. The next one is going to be a W12. And then there's going to be a W13, etc. So these are now the parameters which we want to optimize. Furthermore, the hidden nodes connect to the output nodes in the same way. So we are going to call this a fully connected neural network in the sense that all the nodes are connected to the nodes in the next layer. There is normally in a standard so-called feed-forward neural network, there is no connectivity between the nodes in a given layer. So that means that the hidden nodes, they do not communicate with each other. So let's mark this so this is normally what we call a fully connected network. There is no connection between the nodes in a given layer, no connections. Between nodes in a given layer, we can actually change that. And you will see that there are complicated models like Boltzmann machines, or we can have some of these variational autoencoders, which can actually have connections within the layer itself. This normally complicates the training process. So no connection between nodes in a given layer in a specific layer. Now, just to stay with this kind of overarching picture, so what we have depicted here is normally called a feed-forward neural network. This means that what we are doing now is that we are initializing these weights, and this is typically done by assigning some random values to the weights. And then we produce the connection between the output layer and the hidden layer. So the different parameters which we have, they allow us now to produce a new input to a given node in the hidden layer. And then this input produces an output, and this is forwarded to the next layer, and so on and so on. So this is what we normally call the feed-forward process. Now, the feed-forward process reaches at the end the output layer. This output is then compared with the target values which we want to reproduce. Then, since this does not include any training of the weights and the so-called biases, then we need something which is called the backpropagation algorithm in order to train the weights and the biases. That means the parameters of the model. So let's look back a little bit here and add some more stuff to this graph, which we have plotted. So every one of these nodes, which you see here, they produce an output. And I'm going to set up the mathematical notation for the given outputs a little bit later here. So every one of these produces an output, and that output is fed into the next layer. So that means that in here, there is a function which takes in the information from the previous layer and produces a new output in the hidden layer. And we normally call this the hidden layers because we are never concerned with the explicit values here. What we see when we are setting up a neural network is the input and the output. So what is in between are mathematical operations which we never see the explicit output of unless we want to print these outputs. So let's proceed a little bit with further details and all the kind of technicalities and details which we now need to set up a fully connected neural network, which is given by what we normally call a feed-forward neural network. So what we are going to deal with is a feed-forward neural network, feed-forward NN. And this now needs, if we now look at a given specific hidden node, so let's now think of this as a specific hidden node, and let's call this a node HI of a given layer. So now I'm not looking at a specific layer 1, but we are going to have a hidden layer L, and I'm going to make this a little bit shorter to not have too many things to deal with. So when I put the superscript, that refers to a given layer. So this is layer L, and this is refers to the subscript, refers to node I in that specific layer. Now, this node receives input from many previous nodes. So there will be an input coming from the different input nodes from the previous layer. So this could just be the input from a previous layer. So these conspire to produce a value, which I'm going to call Z of I for that specific layer. And that is going to be given by a sum over all the inputs from the previous layer. So I'm not specifying the sum here. So this is running over all the nodes in the previous layer. So I'm just going to write this in an odd way here. All nodes in previous layer. In layer L minus 1. So mark that one. So these are the nodes in the previous layer. And they're going to be connected by variables W, which we are going to call the weights. And these are the parameters we want to define. So this is going to have a J of L here. No, sorry, J of I. And I'm going to put a variable L on top here to indicate that these are the weights which pertain to that specific layer. And these are multiplied with the output from the previous node. So this is a node J from layer L minus 1. So let me mark this one. So this is the output from a specific node from node J in the previous layer of and this could be just the input layer of L minus 1. Now this then has an additional parameter which we normally call a bias. So a B of I of L. So this specific parameter is something which is called a bias. And one of the reasons for why we have this specific parameter is that sometimes these weights could end up being close to 0. And that means that it would not have an input. In order to guarantee that this network is going to have at least some input, we have an additional value, which then guarantees that if we by accident have weight values which are 0, then the network will have an input to that specific node, and it can produce an output. If we don't have this bias, we may actually risk that the training of the network may stop before we want the training to stop. So in this stage, which we are calling the feed-forward stage, what we are doing now is that we are setting some random values for these weights and the biases, and we are just producing now outputs from every single node in the layer, whether these are hidden nodes or output nodes. Now this one then produces an output. And I'm going to call this output for an AI of node I in layer L. So this is what this specific node produces. This is normally called, in the literature, it's called a single perceptron. So you could actually make a single perceptron model, but a single perceptron model would not be able to produce anything but a fit to a linear function. If we now have a hidden layer, we can actually make fits of nonlinear functions. We are coming back to that next week when we are going to look a little bit more at the mathematics of neural networks, and in particular in connection with the fundamental theorem, which is called the universal approximation theorem. So what I wanted more to do today is actually to set up the basic operations which make up a neural network. And when we are done with that, then we are going to go back and look at what this actually means. And then we're also going to build a code for a neural network. So these are some of the basic entities which we end up having to define. Now, inside here, if we now look at this hidden layer, so if you look at that one, inside here, there is a function which now takes the input and produces an output. So if we now just move down a little bit and proceed, so we are going to define a function which is normally called the activation function. Define activation function. And I'm just going to call this for an F. And one of the most standard functions is the sigmoid function, but there are many, many more. And this becomes a parameter in the setup of a neural network. When we are dealing with the architecture of a neural network, the activation function itself is something which we can treat as a parameter. So this function, unless we're dealing with Bayesian neural networks, where we actually use Bayesian statistics to define a probability distribution for every single node, this activation function becomes a parameter which we can play around with. So what happens then is that this output, A of IL, is now given by this function, which takes in this input, set I of L. And this input now is given by this F, and it contains this sum over all the weights, J of I, of this specific layer, multiplied with the output from the previous layer, L minus 1, plus this bias variable of B of I of L. So what we have now are the parameters which we need to define in the theory. Parameters to define. I'm going to call these as a parameters theta. So this is a collective denominator. So we are going to have all the weights, which I'm now going to indicate with a generic symbol W, and all the biases. So these are the weights for all the hidden layers and the output layers. So weights for all weights that connect all layers, connecting all layers. And these are the biases for every specific node in a given layer. So these are normally called the biases. And these are the parameters which we want to train in order to make a model which now reproduces a specific function. Any questions so far, guys? I'm moving a little bit, I'm going a little bit slowly ahead here because I just wanted to bring up the basic parameters which define a neural network. So if we now look at what we are going to have is the following. So when we look at the architecture of a network, architecture of a feed-forward neural network, FF, feed-forward neural network. So what we are going to have is the following. So we have an input layer, and this is fixed. So we never change that one. So in a basic deep learning network, the input is never changed unless you are dealing with something which is called Boltzmann machine, where you can generate the layer, the input layer, the inputs again and again. So these are normally called generative deep learning methods. So the input layer is fixed. And then we have the output layer, which is also fixed, because we have a specific output. If we are dealing with like the classical case of the classification of handwritten numbers from 0 to 9, then we have 10 outputs. So there will be 10 output nodes. So this is normally also fixed, the type of output. This is the most common setup. Then we have a certain number of hidden layers. And this is what we have to decide upon. So this becomes a parameter or a part of our model. So when we're dealing with a feed-forward neural network, the model is defined by the architecture of the network. So in each hidden layer, we have a given number of nodes. So we can have as many nodes as we want, but typically what you would do, you would start with a few set of nodes, and then you would start training the network, and then you find some kind of measure for the quality of your model. And then if you're not happy, you can increase the number of nodes, you can increase the number of hidden layers, and so on. So these become parameters in the theory. Now, what more, when we are looking at these different nodes here, in these inside the layer, we have what we call the activation function. And this function becomes a parameter. So we have this function f of this set of I of L, which could be a function which we normally want to be easy to evaluate, because we're going to calculate this many, many times. We want it to have some specific properties. We also want to have a derivative which is easy to handle. So a typical function, which you may encounter again and again, is the sigmoid, which we encountered when we looked at the logistic regression. So one of the most standard function, and also the function which caused problems in the training of neural networks, is the sigmoid. And we are going to look at examples of how to use that one. So this has a minus set of IL. So the activation function becomes a parameter. What next? We need now to calculate weights and biases. So we have the weights, W. We're just going to call this Wij of L. And these are going to be represented generically by a variable W. We would have the biases, BIL. So these are the so-called biases. These are the parameters of the theory. Next, what we need now is a way to train. So a training algorithm. And the training algorithm is called the backpropagation. And this is the one which we are going to derive after the break. Backpropagation algorithm. That's the central algorithm in a neural network. So we have a feed-forward stage, and then when we reach the final output layer, we compare the output with the targets, and then we propagate back again and update the values of the weights and the biases, and then till we reach the input layer, and then we have new weights and biases. We do a new feed-forward stage, produce a new output, compare that with the targets, and then we go back and forth till we have reached a satisfactory reproduction of the outputs. So the backpropagation algorithm is going to be an essential element in what we are going to do. Now, the backpropagation algorithm leads to the gradient method. So we have a gradient descent because we are going to train the weights. So that leads to a gradient optimization. And this is where we are going to encounter again the gradient descent method. We are going to look at different variants of that. So that becomes also a kind of, how to say, loosely said, a parameter in the theory, because we can do the gradient optimization in many, many different ways. Then we're also going to have regularization terms, like the same terms, regularization. So this will be typically an L1 or L2 norm. These are the most common ways of adding a regularization term. And they tend often to reduce both the bias and the variance of the model. So when we now look at the architecture of a neural network, there are going to be many more additional parameters which we can tune. So the basic parameters are the weights and the biases. But in doing that, we have as parameters the setup of the network, which is defined by the number of hidden layers, the number of nodes we have, the type of activation function which we're going to use, and the kind of gradient optimization which follows from the backpropagation algorithm. So after the break now, we are going to look at the derivation of the backpropagation algorithm, because that sets up the essential elements of a neural network. So everything, if you peel down all the gritty-nitty details, what we end up are matrix multiplications and matrix vector multiplications for fully connected layers. So there is no reduction of the connection between a given layer. So all the nodes from one hidden layer connect to all the nodes in another hidden layer. And the backpropagation algorithm is the one which is going to give us the values of these weights and the so-called biases. I see I went a little bit over time. Is it okay if we take a small break? I'm going to stop or pause the recording. So welcome back, everybody. What we are going to do now is just look at the basic mathematical operations which are needed in order to set up a neural network. So the basic mathematics, so the simpler mathematics, involves now a set of operations which we simply can summarize as a set of matrix and matrix vector multiplications. That's essentially the mathematics of a feed-forward neural network. And then when we bring up the backpropagation algorithm, this is going to allow us to find the optimal parameters of the model. And this backpropagation algorithm is just a simple application of the chain rule. So there's nothing more to it than that. But it's an intelligent application of the chain rule, which allows us to set up the training of the weights and the biases, which are the parameters of the theory. So let's now look at the basic mathematics of a feed-forward neural network. So the basic mathematics, which we need, of a feed-forward neural network. So let me quickly remind you of some of the things which we defined before the break. So we defined a quantity like this activation function. We have these unknown parameters, which are the weights. We have the unknown parameters, which are the biases. In addition to that, we produce, at every stage, we produce an output from a given node. And at the end, we are going to look at the output from the final layer. This final layer is normally called the output layer. And this output is the one which is compared with the numbers we want to reproduce, which we label as the targets. So if we now look at the basic mathematical operations which we have, so what we have a matrix W, which now contains the weights. So we are thinking of just one hidden layer. So this matrix would typically be a real object of dimensionality m times n. So we would typically write this matrix, which now contains all the weights, which connect the nodes from one layer to the next layer. So we would typically have a vector here, W1, and this would go all the way up to the final vector of Wn. So the input then to a specific node. So we can write this in a more general way. So we can look at this as a vector now. So the input to all the nodes in a given layer, and I'm skipping now the specific indication of a layer, is something which we call Z. So we are now thinking of this as something which receives the input from the the input layer. So X is a variable which we reserve to the input layer. So this would now be given by a matrix multiplied with X plus this bias B. And X has now a dimensionality, since this belongs to the input, of n. So what happens next is that this X is now fed into this activation function, which we call F. So F is the activation function, and that produces an output. And we feed that X into that one, and that is given now by this variable Z of X, like this, and that produces an output, which we are simply going to call for a vector A of X. So this vector contains now this vector A of X that contains the output from each single node. And as I said, I'm skipping the specific layer symbol. So we would have a node 1, which receives X, a node 2 of X, and so on till the final node, which we have in that specific hidden layer. So an artificial neural network then cascades this set of operations in multiple terms. So if I now have more layers, so with a total of L layers, now I'm going to use L as a way to indicate the final layer or the output layer. So let me just note that one. So L is the output layer. What we are going to have then is a series of such operations with a total of N layers. So we are going to have a set of outputs which I'm going just to label A of L, and that contains the outputs from every single node from a given layer. And we would have this L to run from the input layer up to the final layer L. So that means that this A1 is actually an operation which takes us from the dimension of the input layer to the dimension of the first hidden layer, N. So that means that if I take a layer A of L, this is now going to take some input from the previous layer, which now is LL minus 1. So NL minus 1 indicates the number of nodes I have in the previous hidden layer. And that brings us to the next layer of N of L. And then for these operations, which we have then, for 2 less than L, so the input layer, remember now that that is fixed. What we have then is a function, which I'm going to call, this represents actually the function f, taking the input with the given parameters theta, which now contain all the different parameters. What we're going to have then is a set of affine operations where I'm now looking at the final activation function or the final output layer. So this takes in A of L, which then in turn takes in the input from all the previous layers. So there's going to be an F of 1, and then I'm going to have my A1, which now receives X. So there's going to be a series of such operations, nested operations. So what you could say now is that the network is cascading through every iteration, not through every layer. It's cascading these operations through the activation function F. So this is the basic mathematics you're going to have for a neural network. And in every such single layer, there's actually a typical matrix vector operation. There is the addition of a vector. This X could also be a matrix. W is a matrix which contains the unknown weights. So in principle, this W times X could be a matrix-matrix multiplication or a matrix-vector multiplication. So these are the type of affine operations which then take place in the feed-forward stage. So the feed-forward stage assumes that you now have some values for these parameters. Now what we need now is actually to find the values of these parameters. And that's where we need the backpropagation algorithm. So let's derive the backpropagation algorithm so that we have all the elements which are needed for us to be able to set up a neural network code. So the backpropagation. So remember now that L, when I use the uppercase letter L, this is my output layer. And that's the one I want to compare with the targets. So what we need to define first now, we need to define some quantities. And these quantities are just helping quantities in order to set up the backpropagation algorithm. So let's look at the mathematics of these quantities. So we need to define some quantities now. What we have done is to define a variable set of J or I of L, which now is the input to a given hidden layer. So I'm just going to write this in a very generic way now without putting up the limits. So it's running over all the nodes from the hidden layer, which we have, the previous hidden layer. So I'm going to have some weights here. So I'm going to have some parameters, ij from the layer L. So these are the weights. And then I have my inputs from the previous layer of L minus 1 plus a bias of BJL. Then I'm defining an activation function, AJ of the output from the given by the specific activation function. And in this example, which I'm setting up now, I'm going to use the sigmoid function. But we are going to replace that with other functions, because one of the problems with the sigmoid function is that that one tends to have derivatives when Z is very large, which can become close to 0. So these derivatives enter the calculations of the gradients. And since these derivatives can then become, depending on the value of Z, pretty small, that means that we can get what's called vanishing gradients. And when we have vanishing gradients, what can happen then is actually the training stops. at an unwanted stage. So that's the problem of so-called vanishing gradients, which we're coming back to a little bit next week. So we have a minus set of j of L. And this function, which you see here, this is what we call the sigmoid function, which we also discussed in connection with logistic regression before the break. This is one model for the activation function. As I mentioned before the break, the activation functions become a type of parameter which we can play around with. And we are going to meet different types of activation functions. Now, what we need now are some specific quantities. So let me just define that. So we have some useful quantities in the derivation of the chain rule and the backpropagation algorithm. So one of these quantities which we will need is actually the derivative of this quantity z with respect to the weights, because we are going to take the derivative of the cost function with respect to the weights. So we are going to have a derivative of this set with respect to the weights. And if you look back at the equation which we have here, so you see now that if I take the derivative of this quantity with respect to wj, I'm simply going to get this ai of L minus 1 as a result. So this is a useful quantity which we are going to need a little bit later. Another quantity which we are going to need, so these are just help quantities, we need the derivative of this input with respect to the output from the previous layer, L minus 1. And if we now go back to the equation which we have here, so the defining equation for the value set, which is down given by this, in principle, this vector matrix multiplication, or vector matrix multiplication, depending on how we have defined these quantities. You see now, if I take the derivative with respect to this quantity, I'm just left with this quantity here. So this is pretty obvious. So what I'm getting now is a wij of L here. Now, another thing which I'm going to need is the derivative of daj with respect. Yeah, go ahead, please.
I think the whiteboard is stuck.
Oh,
So
is the whiteboard? Oh, sorry for that. Sorry. Okay, so let me just bring back the whiteboard here. Let me just, yeah, I see that one. Can you see it now?
Yes.
Okay, so what I would be needing then are these quantities here, and let me just do one small thing here while I do that, because I see that they have a small, there is a small problem here which I have. Let me just redo that one. Okay, let me, so that, and let me also do that one. I see that I have a small, sorry for that, I have a small problem here with my setup of the iPad here. Sorry for this, right? Let me just bring this one up. I just need there's a small thing I need to fix here. Can you still see the whiteboard here?
Yes, we can, but could we also ask you to scroll up to the line, define some quantities? Yeah. Because so that's where it got stuck.
Yeah, so let me just bring this up here. Let me just see, I have, there we are. I just need to bring up some of these small things, just a small moment here. Okay, so the, just take that one. There we are. Okay, so let me now just see. Can you can still see it now, right?
Yes.
Okay, so let me just bring this up here and just repeat it. Sorry for that. I actually, I think I touched another screen here, and I was so obsessed with my whiteboard that I didn't see that things had changed on my main screen. So what we are defining, so let me repeat this. And we define some quantities, and the quantities which we need to define is the input to a specific node, and that is given by this affine transformation. So we have the weights given here and multiplied with the inputs, or rather the outputs from the previous layer. And then we have the bias here. So these weights and biases are the parameters which we need to define. Then we have the output from a specific node, which is then given through this activation function, this f. And these activation functions, they become like parameters in the setup of a neural network. And in this specific case, in the derivations here, I'm going to use the sigmoid function, but later we will replace that one because the sigmoid function has a drawback. And you can easily see that when you plot the sigmoid function and you look at large absolute values of the argument set, because then the sigmoid function is going to be pretty flat. When you then calculate the derivatives of the sigmoid function, you can risk that the derivatives can become very small. Now, these derivatives are going to be essential elements in the setup of the backpropagation algorithm and the computations of the gradients. So that means that when we now compute the gradients, we can actually risk in the training process itself that the gradients are going to vanish at an unwanted stage. Now, the thing which we need now are some help quantities. And these are some quantities which we are going to use as intermediate calculational steps in the setup of the backpropagation algorithm. So one of the quantities we need, since we are going to take the derivative of the cost function with respect to the weights, we need this help quantity here, which you can see is equal to what we have here. If you now go to the expression for z, so if I take the derivative of z with respect to w, you see now that this simply gives us this parameter here. Similarly, if I take the derivative of z with respect to this quantity, what I'm going to get now are just the weights given by this equation here. So these are just two help quantities. Now there is a further help quantity which we need, and that is the derivative of the output with respect to its input. So a typical function which we are going to use is the sigmoid function. And if I take the sigmoid function, which is given by this function here, it's easy to see that this derivative of this quantity here with respect to z is simply going to be equal to a f of z j of L multiplied with 1 minus f z of j of L. And we can rewrite this in a more compact form as aj of L of 1 minus aj of L. Now, this derivative will change depending on, it depends on the type of activation function which you have. So clearly, this is one of these parameters which we need to make more, how to say, flexible in the code in case you want to change activation functions. So the activation function becomes a parameter in our theory. Now, what we are going to do now is to use these quantities in order to calculate the derivative of the cost function with respect to the weights and the biases. So now we are going to look at the cost function, and this is defined at the output because it's the output which I now compare with the targets. So this will be a set of contain a set of parameters which are called theta L and uppercase L to indicate that this is my output layer. So this is going to be a function of the weights at the output layer. So these are the weights which are connected with the last hidden layer. and it will have the biases as a parameter. And if we now look at what we did, if we look at the regression problem, so now I'm just defining that. And next week, we're going to look at what happens when we have a classification problem. So now we take a regression problem. And in that case, we are going to look at the cost function defined by the mean squared error. So there's a sum 1 up to n here, and then I have my y of I, and this y of I is going to be equal to a of I of L minus the targets. So these are fixed, and this simply becomes equal to 1/2 of I equal 1 up to n of AI L minus T of I squared. Then what I want to do now is to take the derivatives of the cost function with respect to the unknown parameters. So the first derivative I'm looking after now is the derivative with respect to the weights. And now I'm just specifying the weights JK at the final layer L. And if I look at the derivatives, then obviously, if I take the derivatives of this specific function here, what I get then when I use the standard chain rules and everything, what I get now is an A of JL minus TJ multiplied with D of AJ of L of D of WJK of L. Now, again, I'm going to use the chain rule here. And you see now that if I take DAJ of L with respect to the weights here, JK of L, then I can again use the basic chain rule here, and I can rewrite that one in terms of the parameters set J, which I have, and D set J of L of D W JK of L. And these are the two parameters which we defined a little bit up here. So if you look at this specific parameter here, this one, we defined that one up here, that is help quantity. So we have it here. This is generic. It becomes specified by the specific cost function. It does not depend on the specific activation function. And then I also have the other quantity, which is this one, which I need, which is now more specific because it depends on the derivative of the specific activation function I have chosen. So it means that if you write a more general program, what you would need to do now is actually to have a list of activation functions and then have a list of derivatives according to the type of activation functions. But let's stay with the sigmoid function. And then we see now that this quantity here is a quantity which I can write out as an AJ of L minus 1 minus AJ of L of AK of L. Sorry, this should now be an uppercase L. So this is the last layer before the output layer. So with these quantities, we can now move on and we can set in the final expression for the derivative of the cost function with respect to the weights in the output layer. So I would have a specific weight, JKL. We can obviously rewrite this as a matrix in terms of a matrix vector notation, but I'm now just going to keep the explicit indices here. So that's going to be given by my AJ of L minus my targets. These are the values I want to reproduce, times AJ of L, and then 1 minus AJ of L multiplied with the output from the previous layer. Now, it's pretty common now to collect some of these parameters in terms of a quantity which is called delta JL. So we can actually rewrite this one in terms of a parameter, delta J of L. So these values, except for the last parameter. And if you now look close at that one, what you have then is actually an expression which is equal. So this, if we take this delta j of L, you can rewrite this one as an aj of L, 1 minus aj of L, multiplied with aj of L minus tj. Now we can make this more general, and we can rewrite that as the derivative of the activation function, ZJL, multiplied with the derivative of the cost function with respect to the output in the last layer. So this is a little bit more generic, and what I've done here is just to keep this specific sub-indices, subscripts, and you could obviously rewrite this in terms of a matrix vector operation or matrix or vector-vector operation, depending on the dimensionalities which are dealing with. So this parameter delta J now defines an essential parameters in these derivatives here. So if I want to compactify it, I have something which now depends on my activation function, which is this term here. I have something which depends on my specific cost function. So if you write a general code, you see now that what you could have is just a list of derivatives of various activation functions. And then you could also have a list of cost functions. So the expression is very generic, as long as you have a list of specific cost functions and specific activation functions. Now, what we have then, if we now collect this, is that we have a d of derivative of the cost function with respect to a specific weight in the output layer, which we can rewrite in terms of this parameter here, which now is defined by a specific cost function and a specific activation function, multiplied with the output from the previous layer. So we would have a k of L minus 1. Now, there are some further manipulations which we can make now. So if we look at this parameter delta J, so I'm just setting up these parameters, these equations. So this is now given, and it's easy to see that I can actually rewrite that one in terms of set J of L, which is the same as a cost function in with respect to J, AJL of dAJL multiplied with the derivative of A with respect to Z. This is actually something which becomes very useful for us, because we can actually show then, by using this derivative operations, that this is actually also equal to, and I leave this as a small exercise to you folks, that we can actually rewrite this in terms of a derivative with respect to the biases, which are the other parameters. So we would have a BJ, L, and it's pretty easy to see that when you look at the equations here. And this is now the same as a D of C with respect to dBJ of L. So this parameter which you have set up here is a very interesting parameter, because we can relate that one, this delta JL, directly to the derivative of the cost function with respect to the weights and the biases. So for the weights, we have an equation which now will depend on the input from the previous layer. And then we have a function here where we can relate only the delta JL to the derivative of the cost function with respect to the parameters beta, no, sorry, B, the biases. So what we have here are two essential equations which are going to make up a central part of the cost of the backpropagation algorithm. So we have the derivative of the cost function with respect to the weights at the last layer, and we have the derivative with respect to the biases at the last layer. So these are two important equations which we need. Now, the next thing which we need now is actually to propagate backward. So we need now, what we would like to have, in order to perform this training, we need delta J of little l. So we have found the derivative with respect to the output from the last layer, and we compare that directly with the targets. But now we would actually like to set up an algorithm which also allows us to find the weights and the biases in the layers before the final layer. So what we are going to do now is actually to go back to the equation which we had for delta J of L. So we have a delta JL, which is now, if we now go back to the equation which we put up here, we know that we can now put this one, if we look at the equation which we have here, so we can use the expression with respect to Z. So what we are going to need now is another equation, which is not so difficult to show. So this is going to be given by set J of L. And we can then use the chain rule again to define this value at the previous stage. So what we're going to do now is to make a sum over the values of set taken at the layer before. So we're going to have a set K of L plus 1. So this is just a repeated application of the standard chain rule of set K L plus 1. And then derivative with respect to set J of L. So we are using the property which you see here, which follows from what we observed in the final layer. But now we are going to look at a specific layer, and we're going to backpropagate these values. Now, if you look at this quantity which we have here, this can now be rewritten in terms of a quantity which I'm going to call D of K of L plus 1, where we now follow the similarity which we see here. So that defines a quantity. So if L plus 1 is equal to the output layer, we have the expression for that, as we demonstrated above here. This is now something which we can rewrite in terms of this quantity which we don't have yet. L plus 1 of dz of J of L. Now, one of the things we know then, however, is that this set K of L plus 1 is actually given by the input from the previous layer, and we have the weights. So what we would have then would be some parameter ij, and then we would have the layer, the weights of a layer L plus 1, and this is then multiplied with the outputs from a specific layer. So sorry, I had a parameter here. It should not be K here, but it should actually be J, like that. And then I have my previous layer plus Bj of L plus 1. Now you see now if I take the derivative of this quantity here with respect to this quantity Zj of L, then we can easily find that this parameter here, delta J, so this delta J of L, if I use this the last expression here, this is something which I can rewrite in terms of a delta K of L plus 1 here. And then, so there's a sum over K here. And I can rewrite that one in terms of a WK J of L plus 1. But now, when I'm taking the derivative with respect to set JL, the quantity I have to be a little bit careful with is actually this quantity here, which now depends on set JL. So what I end up with is actually to have to take the derivative of the activation function in the layer, in the previous layer. So I would have a set J of L. So again, I need a table of derivatives depending on the type of cost function which I want to use. So what happens then is that I'm going to have a final equation now, which allows me to set up these derivatives. So I'm having a general expression for delta J of L, which is now going to be given by f, the sum over k over delta k from the previous layer, L plus 1. And then I have a wkj, the weights, the unknown parameters, of j plus 1 multiplied with my activation function of set jl. I have the value at the output layer, which is defined by this f of zjl times the derivative of the cost function with respect to the output from the last layer. So I would initialize everything in this specific way. And now, in this particular case, what I would have is that L starts with L minus 1, goes to L minus 2, and then it continues down to the final hidden layer, to L equal to 2. The first layer is now our input layer. So with these values, we can then compute the weights and the biases at every hidden layer. So for all L, from L minus 1 down to L equal to 2 here, what I have is the following recipe. So I have a wjk for a given layer L, which is now being updated with the value, the previous value, minus a learning rate. And then I have the gradient. And the gradient, so my gradient for the weights at a given layer are going to be given by this function, delta j of L times the output from the previous layer, L minus 1. Similarly, the update for the biases of bj of L are going to be given by this iterative formula, where I'm just setting up everything for the gradient descent, minus eta times the derivative of the cost function with respect to this bjl. And this is going to be given by bjl minus eta times delta j of L. So the equations which you see here, these equations are the equations which we need to set up to backpropagate the unknown parameters. So this is the backpropagation algorithm, the mathematical expressions for them. And what we need now is a gradient descent in order to find the optimal parameters. So the backpropagation algorithm gives us the equation. So let's just mark that. So these are the equations which we need. But then we need the gradient descent to find the explicit values. And this is what we're going to discuss next time. To find the values of bjl and wjk of L. Okay, I'm going to stop the recording here now. And this concludes the derivation of the backpropagation algorithm.